together for the first time, explain all together what's going to be happening with these Laplace transforms. So what's going to be happening is you have over in what's called the time domain, but it could also be the x domain, because like say with beams it'd be x. So it's called the t or the x domain. And what you have is a differential equation. Now what you want to do is you want to solve for, say, y of t or y of x. Okay, now that can be a difficult problem. It's the shortest, well, as such, looking at this picture, it's the shortest path, but it's a difficult problem. So what we do instead is we translate the problem into the S domain with what we call the Laplace transform. So the Laplace transform takes the differential equation and turns it into an algebra equation. And the algebra equation is very, very easy to solve. So whereas this can be kind of, this might be hard here, getting from here to here, it's very easy to solve an algebra equation. So the solution is y of x, y of s. That's easy. Now, obviously, there's no free lunch. So the difficult part, which we could describe as medium difficulty, perhaps, is that you translate back. And that's probably, we'll call it medium now. It's hard. There's no two ways about it. But a lot of the time, so you do something kind of, you do a Laplace transform, that's easy. Turn into an algebraic equation, solve that, that's easy. And then you've got a medium difficulty thing. So it seems a very roundabout way of solving the problem, but it works very well. And often when the differential equation is nearly impossible to solve, this will work. So in terms of, to give you an analogy, so this is the analogy and we'll see it again later on. So the differential equation is going to be a poem written in English. And what we'll say the solution of the poem is the meaning of the poem written in English. Okay, so I don't know about you, but I'm crap at poems. So, but maybe there's a French person who's very, very good at understanding poems. So you translate the poem from English into French. So this is the poem, basically the same equation, but written in a different language. And then you have a French friend who's very good at getting the meaning of a poem. So that bit's easy for them. So getting the meaning in French is solving the algebra equation. Then you just translate back to English. So rather than you finding out the meaning of the poem, you translate it into French and a French person understands the meaning, and then either they translate it back to English or you translate it back to English, you've got the meaning of the poem. So that's the big analogy. Okay, so this is why we're studying Laplace transforms, to solve differential equations. So if we look at let's see this last exercise, I'm not sure what this is all about. I'll have to find this. I don't know any exercise. Ooh, I'm gonna have to pause this. So there is no such last exercise. So let's go to page 105. So you look at these things on the left. This is what, when you solve the algebra equation, this is the kind of things that you'll get. So these are all what are called rational functions. These things are called rational functions. They're a ratio of polynomials. So I think I call them P over Q. So they're all of the form a polynomial divided by a polynomial. So for example, for this one, the top polynomial is 2s plus 8, and the bottom polynomial is s squared plus 14s plus 49. So when you get down to this point, the big Y of s, you'll find that when you solve the algebra equation, you have what's called a rational function. Okay. Now the problem is, if we look at our tables now, I think I'll probably have to pause this and find some tables to show you. Okay, we're back. So this is the tables I'll have to send this on to. Well, let me zoom out for some reason. So a lot of these we've seen before. Constant is sent to constant over s. A power of t is sent to this thing. Now the next one is also a power of t, but it's just if you're sending it back, I don't know if I can write on this. No, I can't. It's easier to send this back rather than that back. So that's why that's there. Negative exponential goes to 1 over s plus a, sine, cos. Then the next thing is the first shift theorem, and the last two things are the derivatives. So these are all the things you have in the tables. So if I come back here and look at page, say, 105 again, these things on the left are not in the tables, the things on the left. So the rational functions are not in the tables. So what you have on the right are things that are in the tables. So this is in this is in the tables, this is in the tables, this is there, this is there, this is there, this is there. This is there. This one's a bit hard, but it's there. This is there, this is there. They're all there. Okay, so in particular, let's just kind of, now I've taken the tables away, but what's in the table is constant over s. That's that sorted, that sorted, that sorted, that sorted. The next thing in the table is 1 over s plus a, which includes minus a. That's that, 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 that. The next thing in the tables is s over s squared plus omega squared. So that's that sorted. And then the last thing that we look at is a combination of two things. So we have 1 over s to the n, and then a shifted version of that, 1 over s plus a constant to the n, is kind of in there via the first shift here. And that would be, that's this. That's this. Okay, so writing the rational function, that's the thing on the left. So you got this complicated thing, you need to write as a sum of simple things. Doing this is called doing the partial fraction expansion or decomposition. Partial fraction, I'm going to go with expansion. So your job is, once you've solved that little algebra thing, you want to send it back, but the stuff isn't in the tables, you have to write it as a sum of simple things. So that is going to be your job. So the job here, looking at the answers to the, should probably say next exercise, all the Laplace transforms are all rational functions. So what we want to do is we want to write this thing ideally as a sum of simple things. So we'll write this as a sum of simple things. Now the method is something a little bit like the following. So you can add fractions together. So for example, 1/4 plus 1/3, you can write them both over 4/3. So you can write this 1/4 by 3/3 plus 1/3 by 4/4. Now what's important here is that the 3/3 and the 4/4 are equal to 1. So while the thing on the right of the equality looks different, it actually isn't. So then you end up with, how do you multiply fractions? Top, top, bottom, bottom. So you get 1/3 is 3/12 plus 1/4 is 4/12, and so you get 7/12. Now that's kind of we're thinking of these things on the left as somehow simpler. So these are somehow simple because they're lower. They're fours and threes rather than 12s. So really, I say simple. Really, I want to say it's a sum of simple, and this is something that's somehow complicated. Now, this is writing a sum of simple things as complicated. What we're going to be more interested in is taking a complicated thing like 7/12 and writing it as a sum of simple things. So we want to go from complicated to sum of simple. And all the simple things, when we look at it, are going to be in the table. So we'll look forward again. So if you look at all the things on the left here, these are complicated things. And on the right, we have sums of simpler things. So this is this partial fraction expansion. Okay, right. So we're going to show, okay, now one of the things is actually you can write 7/12 as a sum of quarters and thirds in loads of different ways. I can't think of any off the top of my head here, but there are loads of ways you can do it. So I'm saying that it's not unique. 7/12 as a sum of quarters and thirds. There's loads of ways. Maybe if it's something like, I don't know. I can't do it off the top of my head, but there's loads of ways. But what we're going to do is we're going to do it so that it's done in a unique way. Okay. So you've got your rational function. So for we'll give an example of this. So for example, something like 2s plus 4 over s squared plus 8s plus 16, say something like that. The first is ensure that the degree of the bottom is bigger than the degree of the top, but that's actually always going to happen in this module, so we won't worry about that. What you do first then is you factorize the bottom, and this is where we're talking about in the last chapter. In this, it's not so interesting to solve it equal, or important to solve it equal to 0, it's to factor it. Now, if you're stuck, I'll give you a thing. So suppose you've got as squared plus bs plus c, and suppose b squared minus 4ac is bigger than or equal to 0. Now, if the b squared minus 4ac is negative, well, we'll look at that afterwards. Then what you can do is you can use the minus b. Now, it's a bit messy here because you have to take out the a. So this would be equal to take out the a, and then I'll have to adjust this thing here. So take out the a, and it'll be s squared plus b over a times s plus c over a. And I think what we do, the b squared minus 4ac is basically the same. Yeah. So, okay, so do this and solve using the minus b formula. For s equal to, say, alpha and beta. Then it turns out that this as squared plus bs plus c is equal to a times s minus alpha times s minus beta. So technically it is possible to factorize using the minus b formula, but I just don't recommend it. Okay, but you can do it. Now, if b squared minus 4ac, and we will go into this again, if this is negative, then if you think about the minus b formula, you're going to have a square root of a negative thing. So that gives you an imaginary number, which ends up giving you a complex number. So if you get this, there are no real roots. And that means there are no real factors. Now, you can factorizing using complex numbers, but we're not going to go down that road. And this is all hinging on something called the factor theorem, which we will see again, theorem. it says that if p is a polynomial, so that just means sums of powers of s, like as squared plus bs plus c. If p is a poly, then k a root, I'll write what that means, exactly when, now it'll be a polynomial s here because we'll be dealing with s minus k a factor. I think we'll write this down again, so don't be too worried. Now what does k a root mean? It means it's a number you put into the polynomial and you get out 0. So if you have a root, you have a factor, and if you have a factor, you have a root. So if there's no real roots, then because roots automatically give you factors, there's no real factors. So you can factorize something with b squared minus 4ac, but it'll be with complex numbers, but we don't want to do that. Okay. At any rate, what you have to do is factorize the bottom. Now the whole way through, I'll be recommending factorizing using the AC method, and in every example I do, and we're going to be doing this for weeks, I will use that AC method. If you can do it in your head and get it right, no problem. But what's not really acceptable is factorizing wrong. It's just, no. Okay. So let's see what we have next. So the first step basically for us is factorize the bottom. Okay, so you got this complicated thing, this yoke, and you want to write a sum of simple things. The first step for us is to factor the bottom. Okay, now what happens? So each factor gives us something in the partial fraction expansion. So if we have a non-repeated linear factor of the form as plus b, then we get something like this. So if we have an a times s plus b, this will give you, in the partial fraction expansion, and it'll be in examples that this makes sense, a constant, well, we'll maybe color the constant differently, as plus b some constant. Okay, so we'll do an example. So suppose you have a big f of s is p of s. Now it doesn't really matter what p of s here is at yet. So let's just write it down. So p of s over s plus 1 times 2s plus 1 times s plus 2. So we have to recognize this thing on the left as it's complicated. We want to write it as a sum of simple things. Now what the partial fraction expansion says, that it's possible to write this as a sum of simpler terms, and each factor gives us a different term. So this one, it'll be a sum of 3 terms. So off we go. So the first one, it'll be something over s plus 1. Then it'll be something over 2s plus 1. Now they look familiar, but they're not the same. Plus something over s plus 2. Now it probably shouldn't be a deal for us, but s plus 1 is different to 2s plus 1, but s plus 1 is essentially kind of equivalent to 2s plus 2, because the second thing is twice s plus 1. So what I'm saying is, if you factorize and you have an s plus 1 and the 2s plus 2, you could factorize that a little bit further. And so, like, what I'm saying is, if you got s plus 1 times 2s plus 2, you could take out the common factor. You have 2s plus 1, s plus 1, and this would be repeated. And a repeated one is rule 2. This is related to the fact if you have a repeated real root in the auxiliary equation, when you're doing undetermined coefficients, chapter 2, you need to change one of the solutions. We're going to see something like that. Okay, but anyway, 2s plus 1 and s plus 1 are different. They're not like that. If you want to test for the different, usually it'll be kind of obvious, but find the roots. So the root of s plus 1 is minus 1, and the root of 2s plus 1 is minus a half. They're different. Now for these, anyway, they're distinct. They each get a constant. So this one can take an a, this one can take a b, and this one can take a c. Now it will be our job, and we'll find out later on how to find the a, b, and c. And the big news then is that all of those terms on the right are in the tables. Okay, so that's rule 1. About if it is repeated. So the rule for a repeated linear root, so that's an as plus b squared. Now, like before, if you had an as plus b, because one of the first factor is as plus b, and another as plus b. Similar kind of ideas to chapter 2. If there's two factors, there should be two things in the sum. And if I put in, say, an a and a b over here, then the truth of the matter is I could actually, that's actually just a plus b over as plus b. It isn't two-dimensional, it's only one-dimensional. It can't work. So similar to chapter 2, you have to change it. Now, the change that has to happen here is, and now why is this the case? You probably have to Google this. I can't explain this fully. Is that this has to be squared. So that's how rule 2 works. Okay, and they're different now. Right, let's see an example. So again, suppose you had, again, the top isn't so important at this point. And suppose the bottom is 2s plus 1 times s plus 2 squared. Now, look at the number of factors here, 1, and then the square is 2. So we should have a sum of 3 terms. Oh, I want to go back and just do one thing. So in this thing here, we're going to say that the left-hand side is equal to the right-hand side for some selection of values a, b, c. So we will be saying, I want these to be equal. Okay, that may or may not be notation that I used before. Okay, so here anyway, so there's going to be 3 terms. So there's definitely going to be something for 2s plus 1. And you could say, oh, there's going to be something for s plus 2. And s plus 2 is there twice. So I have s plus 2 there twice. But that won't be the whole story, because if I put an a here and a b here and a c, in fact, what you can see is if you add the things together on the right, you don't necessarily get the s plus 2 squared. And anyway, at any rate, this second thing, if I come back and actually, if I come back actually here, what am I trying to do? Say this is a rule 1 and this is a rule 2. Now, the use of the yellows and the greens is different here. I'm saying the green is it's a rule 1 and a rule 2. Whereas the yellows are saying, oh, there's 1 factor here, there's 2 more, there's 3 factors in total. But anyway, the rule 2 says you have to change one of these to a square. And again, what I want is I will want these to be equal. Okay, so that's rule 2. Then the third one is when you can't factorize the bottom, when you get to a quadratic like an s squared plus 1, which you can't factorize anymore because it has no real roots, you do a rule 3. So the rule 3 says if you have an as squared plus bs plus c, rule 3, okay, so it'll be 1 factor, so you get 1 term. And what you put on top is an as plus b. So you could talk in terms of, see these things, like the 2s plus 1, the s plus 2, they're degree 1, and the constant is degree 0. And here you have degree 2, and it's dividing into a degree 1. Now you could ask about what about an s cubed, but you can always factorize an s cubed into a quadratic and a linear. We might write that down somewhere, probably on the previous page. Is there any good place? We just leave it said. We'll just put it in this little gap here. So you can always factorize if you have a cubic. So if you have a cubic, so something with an s cubed is a cubic, and a cubic can always be written as a linear. Well, I can't use the letter a. Well, I can write s squared plus, say, cs plus d. In other words, you can factorize a cubic into a quadratic and a linear. You won't have to do that. Well, you might have to do it if it's like s cubed, s squared, and s, and you just take out the common factor of s. But in general, we won't be pushing you that hard. But just if it was a question, what about a cubic? So you don't, for a cubic can be reduced to a rule 1 and a rule 2. So a cubic is a rule 1 and a rule 2. It could actually be 3 rule 1s. If the quadratic, the rule 2, can be factorized further, a cubic can be 3 rule 1s. It's probably more. Well, Okay, so let's do an example here. So again, if you have P of S, which is not important at this point, divided by S plus 1 times 2S squared plus 3. Now we have a question here. Can you not, maybe you can factorize 2S squared plus 3. Well, we'll talk about it probably a bit more later on. Well, let's look at it this way. So let's look at AS squared plus something positive. Do it here. So AS squared plus something that is positive. So remember, every root gives you a factor. So let's find a root of this. So solve this equal to 0, and that'll give us a factor. So take away the b from both sides. No, actually, I need a to be positive as well. So both a and b strictly positive. Then you get s squared is equal to a negative number. And there's no real number. So if I use some heavier maths, not in the real numbers. So, no, sorry, that's not right. So there's no number, there's no real number that squares to give you a negative number. So that means that as squared plus b, where a and b are positives, like 2s squared plus 3, is never equal to 0 for a real number. So it has no real roots, so it has no real factors. We will touch on that again in the notes. So a lot of these things I'm doing in blue will be touched on again. You will have to hear them more than once. It's hard enough maths. So anyway, if we come back here though, and we're looking at this, we've got a rule 1, and this is a rule 3. It cannot be factorized further. Now you might say, oh, what if I have a quadratic and I don't bother factorizing it? Oh, trust me, you factorize it if you can, because it's a lot harder when a rule 3 is a lot harder. So this will be equal to, so there's two factors, so there's going to be two things in the sum. S plus 1, 2s squared plus 3. And what does rule 1 say? It'll be a constant. And rule 3 says it's a multiple of s plus a constant. Now I can't use a again, so I use bs, be a little less, bs plus c. And I want these to be equal. Now a good question would be, well, can I maybe just factorize using complex numbers? You actually can do that, but things get a bit more complicated. Like what happens is, so say, like for argument's sake, so suppose you have 1 over s squared plus 1. That can be factorized as 1 over s plus I times s minus I. And then you say, oh, I've got two rule 1s, which is fine. Rule 1, and they're different. And you say, oh, I want that to be equal to something over s plus I, which we'll get back to here in a sec, plus something over s minus I. And those somethings, because they're rule 1s, are constants. But you're getting into a world of pain because the a and the b can be constant. And if you send the s plus I back, it'll go back to e to the it. And then you're into this kind of business with the cos t plus I. You're getting into a world of pain. So while it's mathematically very cool to use the complex numbers, you're not going to do it. If you can factorize it, you can factorize it, leave it at that. If you can factorize it, you do factorize it though. Okay, right. So now the question is, how do you find all these constants, these big A, B, C's and stuff like this? Okay, so what you do is you take the partial fraction expansion. Now maybe I'll just color some things here so you can see what I mean. So write the partial fraction expansion, say something like this, as a single fraction and compare it with the original thing. Okay, so looking at this thing on the right here that I've highlighted, you write that as a single fraction and you compare it to the thing on the left. And what you do then is you set the two things equal to each other. So you're going to write u of s equal to v of s. Now this will be explained better in examples. Now there is, by the way, a rule 4, but it's not examinable. And rule 2, it says there includes higher powers, but it's not an example. Okay, so what you do, the first thing is you can, so you got, now again, we'll see this in an example. So what you can do is you can plug in different values into both of these polynomials. Like, look, if I better do an example first. Yeah, I'll do an example. This probably makes more sense. Right. So find the partial fraction expansion list. So you look in the tables and you want to send this back. It's not there. Actually, I think this video is long enough. I'll go into another one.